My name is Alexander Koropkin. I was asked to chair this session. There are two presentations in this session and one discussion section. I understand that our participants are still coming, so there will be more of us. But also, I cannot see the second speaker.
It's me.
You!
Yeah.
It's Manish.
Then Manish will come.
Oh, okay. Yeah. So you are co-out of that first talk, but the second one, I hope he is coming. Right? Yeah, okay. Then we'll start our session, and the first presentation is by Frank Smith from University College London in Parkside Growth and Related Modeling. 1 hour together with the question, please.
Thank you very much. My colleague David Bella will give the second part of this talk. I'll be giving the first part, and it's on aircraft icing, droplets, impacts, and ice growth. Droplets are very important in aircraft icing, and so there's a lot of research on that. Before we come to ice growth, just before handing over to Davide. It's joint work with a lot of people here, and it involves modelling, computation, analysis, and comparison with experiments wherever possible. So aircraft icing then tends to occur, or can occur, during flights through clouds in which there are supercooled water droplets, and they impinge on the front of the aircraft and produce freezing. All right. So the supercooled water droplets impinge upon the front of the aircraft, air vehicle, and water either then freezes immediately or spreads along the side of the aircraft, or some of it will go into the wake downstream. So the way it freezes has a profound effect on the shape of the icing on the front face of the aircraft or the wing, and we can see that here. Typical shapes produced either for rime ice or glaze ice. Rime ice is when the droplets freeze immediately. Tends to be the smaller droplets, and it's fairly smooth shape, but has the typical two-pronged forward-facing shape, which is gives very poor aerodynamic performance. Likewise, the glaze ice is basically two-pronged, but is much rougher. If we're trying to model some of this, then there are many important parameters involved. There's the droplet size and shape, also the temperature and speed of the oncoming air, and how much water content is in the cloud you're going through, and then the local geometry, the shape of the wing or the fuselage. All these things got to be taken into account, but despite all that complication, engineering models can do pretty well. So here's a set of comparisons between an engineering model, which is TRAG-ICE 2, which is set for very confined circumstances and knowing a lot about the oncoming flow, but it does remarkably well in these three cases in comparison with some experiments done at NASA a couple of decades ago. The experiments are the dash curves, the solid of the model predictions, and it's very good over quite a temperature range, -6.6 down to -16.6 degrees centigrade. So those are the existing models. They work very well for smaller droplets, but not if the droplets are 40 microns or above. So that brings us on to droplets, which are significant, have a significant effect during all this, especially the larger droplets which produce splashing. Larger means 40 to 400 microns, typically, and the engineering models then struggle, believed to be due to splashing and the consequent effects further downstream on an aircraft or on any structure. And so a lot of research as a result of all this has been on droplets and related phenomena like impacts of droplets, impacts of bodies as in lumps of ice on the aircraft, and skimming problems where lumps of ice skim along the surface. All of these things are also of intrinsic interest, of course, scientific interest. Some of the scales and sizes are interesting. So the droplet diameter we've talked about, 400 microns maximum. There's usually a water layer on the aircraft surface of previously deposited droplets, which is 40 microns at most, say. The time scale is remarkably short, 10 to minus 5 seconds. The approach speed is 100 meters per second, say. There are many factors. When we non-dimensionalize, the Reynolds number and Weber number typically turn out to be of the order 10 to the 4, 10 to the 5. So that suggests that inviscid theory could do well, except if we get into boundary layers, for example. And surface tension can be neglected, except if we go down to small scales. Or small scales and boundary layers, of course, are involved in droplet impact, as it turns out. So I'll be talking now about some computations and also some analysis aimed at trying to understand some of the phenomena here. In this computation, it's done by the VOF, volume of fluid method, which we heard about previously this week. And we have a droplet just impacting upon a water layer. The droplet was 4 times the diameter compared with the height of the water layer, and produces a typical splash phenomenon as shown there. A lovely corona shape. And one of the things we had to look at was the makeup of the splash. So this is the raindrop hitting the puddle, and the question is, when the splash occurs, is it raindrop water mostly, or is it puddle water that goes? In this particular case, it's mostly puddle water that's splashed away. The significance as regards aerodynamics is that that means heat is being transferred away from the water layer, the relatively hot water layer, further downstream. So that has an effect on the ice shape further away. And then using these computations, we could then march into parameter space and try to understand some more there. As regards a comparison with experiments, what we've got here are three photos of experiments done at Cranfield. So that droplet looks like a flying saucer. It started further higher up as say a circular or spherical droplet, and impacts upon the water layer and produces this splash here. The corresponding computation is shown on the right here. It has no air in it, so it starts with a droplet of roughly the same size as the experiment and the same shape, and then impact takes place, and the splash that's produced over the same timescales is broadly in the same area. I should say also the experiments and the computations are shown as mirror images. One has the impact from going from left to right, and one from right to left. But I'm not sure which way round it is, but anyway, it's a mirror image. If you measure the angles involved between these two, then they're fairly similar. But it's not so good as the corona develops during the splash. And there are other difficulties involved. It's always difficult to include air, particularly if the airflow is strong, or if the droplet size is relatively large compared with the water. Then stronger airflows are difficult to compute. They can be done. Here's one example on a crude grid where you see an air pocket being produced. But that's still a difficulty. That's because the density ratio of air to water is 10 to the minus 3, and the viscosity ratio is 10 to the minus 2, roughly. So that's immediately an awkward fraction to deal with. And also including surface tension is difficult because of the high Weber number. So to address this then, we turn to some analysis as well, and I'd like to just go through this. So what we have here is a droplet about to impact. It's got diameter 1, normalised to 1, and it's coming in with speed 1. And we're trying to get at an asymptotic solution of the something consistent with the Navier-Stokes equations. And there could be a horizontal component to the impact to give us obliqueness. And we're supposing that the impact is about to take place. There's an air gap here of thickness, typically h, or h squared, we've written it. So the y scale in the air is of order h squared. The x scale would be order h because of the curvature of the droplet. The water layer thickness is of order 1 as well. So given that h is small, we can then build up a picture of the presumably proper approximations in the water and in the air. So in the water, we expect the vertical velocity to be order 1 because of that definition of the impact, of the incoming speed. By continuity, then u is order 1 because x and y are comparable in the droplet. And then the pressure we expect to be order 1 over h, so a large pressure, so that the pressure gradient is dp is of order h minus 2. That then can balance against the acceleration du dt dv dt, which is of order 1 divided by the time scale, and the time scale is order h squared, so small time scale because we're coming in at speed 1 and thinking about a distance order h squared. So we sort of see the equations that are going to come out here, or that we're anticipating coming out. And then in the air, well, the pressure continuity demands an h minus 1 on the pressure. Kinematic condition demands v be order 1 again. And then continuity in this thin gap tells us that the horizontal velocity must be large by a factor h minus 1. So from that then we have, we're getting a fairly complete picture of the water and air combination in 2 dimensions. It works also in 3 dimensions. Then we want to relate that small parameter h to the density and viscosity ratios, which are small. So let's have a look here. We've covered those four lines already. What we get in the water is the equations of unsteady potential flow. So it's full continuity, and then acceleration terms ut vt balancing the pressure gradient, dp dx dp dy. So from that in the water then we're going to get Laplace's equation for u, v and p, as you might expect. So it's all inviscid, but in the air we get a system 2, so full continuity again, but it's possible if the inertia is negligible, we will get a lubrication balance between the pressure gradient and the dominant viscous term dtu dy squared. And pressure is independent of y as it's a thin layer. The parameters involved here, the alpha and beta, are written down here. They involve E, which is the density ratio, so it's a small parameter, and involve the kinematic viscosity ratio and the Reynolds number. So that's what we've got then. That approximation of the neglecting the inertia term works provided the Reynolds number is less than this particular quantity, nu2 over nu1 divided by h squared. When you put in the numbers for air and water into this result here, it turns out to be 10 to the 7. So as long as the Reynolds number is below 10 to the 7, significantly below, then inertia is negligible there, and we're getting this inviscid air is interacting with as a viscous, sorry, other way around, inviscid water is interacting with viscous air in effect. If you remember, fortunately in the aerodynamic situation, that the Reynolds number is order 10 to the 4, 10 to the 5.
You've made some assumption on h, right?
Yeah, just that h is small, and yeah, you're right. It will have to take on some order of magnitude compared to that ratio. Yeah, yeah. Yeah, okay. So the governing equations we get are from the Laplace's equation. It's a Cauchy-Hilbert integral on the pressure, unknown pressure, balancing against an acceleration-like term, d2f dt squared on the left. F is the unknown interface shape or the gap width, and there's a C effect, which is the obliqueness angle up there as well. And then in the air, we're getting, well, we would get Prandtl's boundary layer equations if the Reynolds number of the order 10 to the 7. But for most applications here, the Reynolds number is less, it's just 10 million. So we're getting a subset of the Prandtl equations, namely Reynolds equations, which give us the Reynolds lubrication equation, nonlinear equation between F and P. So two equations for F and P, which we can go ahead and solve. Computations are shown here for a particular case. This is C is 32. The shape F starts as a parabola at a scale time of minus 7.8. So that's the sort of incident condition. The pressure response is hardly there at all, pressure at the wall. So the air feedback is negligible. But at time minus 6.2, we're starting to see a pressure effect developing, which then produces a slight kink in the F shape. That then becomes pronounced, and at time minus 4.8, touchdown occurs, in the sense that F hits 0, the gap width hits 0, and so this droplet is impinging upon the wall or upon the top of the water layer. Okay, and in this particular example, it occurs, time minus 4.8. What that means is the presence of air has produced touchdown earlier than would be the case without air. So in fact, the air cushioning is not slowed things down; it's hurried things up. That's for the an oblique case. If we take a normal impact, so C is 0, then we get a two-pronged impact or touchdown, as drawn schematically here, and so touchdown there and touchdown there, and that produces an air pocket. Okay. I'd like to finish this bit with reference to a very nice paper by Peter Hicks and Richard Purvis and the Russian experimental colleagues. The experiments involve dropping a solid disk onto a water layer and then recording results using a high-speed camera and a mirror. It's the same situation as the one I've been talking about, and here's the comparison of the air pocket radius versus impact speed, a comparison between the theory and the experiments. So it's 4 sets of experiments shown here by the symbols, and there are 4 different conditions, and then the solid line is the result from the theory over a range of impact speeds. The agreement is sort of fairly encouraging, and it would perhaps encourage a view that you could go further out into parameter space to some extent, using the reduced equations I've been talking about. Okay, there are many other such problems involving the behaviour before icing takes place. So droplet distortion is still an open problem as far as I can see, as far as regards a satisfactory physical explanation, why we get to that shape starting from a circular shape, for example. These are experiments from Cranfield again. Droplet impact onto roughness is getting known to some extent, but still of much interest. There are problems involving body hits body, so this is ice lump hits ice lump with fluid flow through them. There's work going on that, so the impact here could be between body and the body, or body and the surface here, or structure surface and we can predict the pressures and shear stresses involved as that body goes badonk onto the surface. And then there are skimming problems, as I mentioned before. As this ice lump has come from the white and gone into the water and then bounced away. So the interest there is in working out under what conditions the bouncing takes place, and under what conditions alternatively does the body sink into the water. Again, it's a matter of the heat transfer involved. Okay, there are some predictions, we'll skip over those. Predictions for the delay involved in skimming. Okay, so last 5 minutes I'll come on to icing and then hand over. So it's a couple of efforts here. One is computational. Again, work with colleagues at Cranfield, solving the Navier-Stokes equations. So it's a full system there. The viscosity is temperature dependent. Using the VOF method again with a Plick treatment of the moving boundary. The boundary moves, of course, because latent heat is let off and the change of state. And then in the impact problems, a droplet hitting a layer of water, you have to decide where icing is going to start. So what we did here is to put a very thin nucleation layer of ice roughness at the bottom of the water layer, which says that icing can take place anywhere underneath the water at the surface, at the solid surface. And here's a typical result. So again, the droplets coming in, and this is showing the temperature field, very similar to the flow field, as you might imagine. And this is for a water droplet at -10 degrees C. The water film was at +1, and there were 50 ice crystals spread along the surface here. Tiny crystals at -0.1 degrees. And the ice crystals were found to grow into each other and smooth out the bed. These sort of predictions can be used for aircraft usage. And then we also, along with that, we used a more analytical approach. Similar sort of problems, so the water droplets coming in there, and it's impacting upon, say, a solid surface on which there may be a roughness already produced by previous impacts and previous ice growth. So the positive time then, the droplet comes down and the contact points spread out to east and west. This is looking at the eastward moving contact point. There's a westward one, some over there, and then we deem in this theory we deemed that the icing could grow anywhere in between those two contact points. Okay, so there's water here, air is here. There's the interface, and then we and what did we do there? Oh yes, we're using here the traditional Wagner theory. It goes back decades, but adding in viscous and thermal effects to capture the ice growth. The parameters involved are here, sort of thing we've seen before, but the Prandtl number, Stefan number, and kinematic underheating parameter are there as well. Some of the main findings are that icing can accelerate or decelerate the spreading of the droplet. So icing isn't just like a roughness. Roughness tends to always decelerate the spreading of the droplet. Icing is more dynamic, so it's not always the same. There are regions of turbulence in the flow. Yeah, let's move on. This is a typical result. So here we have the front, the spreading. There's the contact point which is moving eastwards, and as time goes on, the contact point moves up and over the roughness, and as it does so, it deposits ice behind it here. The amount it deposits depends on various parameters involved. But from this, we can build up a picture of a representative amount of icing that's deposited for a single droplet impact. What we then did was to extrapolate that hugely. So this is occurring over, say, 10 to minus 5 seconds, typically. What we did then was to extrapolate it using the probability that one droplet would impact, whereas previous droplets had impacted previously. What else? The Reynolds number, the water content of the cloud, and so on. And that extrapolation led us to this comparison now with experiments over a longer time scale. So we're talking here about up to 6 minutes, and the build-up of roughness, build-up of ice going into milliliters. And the comparison is with some NASA experiments, which are these symbols here, again 20 years ago. And yeah, the prediction I want to just point out is A, for the conditions of the experiment. The extrapolations is huge. 10 to minus 5 is down here, but we're straight on, we get in line with the experiments, which is kind of encouraging. And then B and C show what you get if the droplet impact speeds were different, or if the droplet sizes were different. We'd get the prediction B and the prediction C. So again, if maybe it's being too cocky about this, but you could use B and C and other estimates to go further out into parameter space. Good. Okay. So that's. I'll hand over now to Davide to talk more in detail about icing. I'll give you that. Yeah.
Can you hear me? I can talk this loud.
That's your voice switch.
Okay. This is on. It's working. Okay, so this is part 2. Compared to what Frank showed you regarding the relationship between drop impacts and icing processes, I will be talking about what happens, icing processes that happens within standing fluids on still surfaces, and specifically the relationship between the geometry of those surfaces and how likely the process is to occur. First of all, icing again occurs it's a problem that is involved in various fields of engineering. One in particular was already mentioned, icing related to aircrafts, which affects the aerodynamics of the aircrafts. But there are also icing problems inside of the walls of machinery like freezers, and that affect the performances of those machinery. And in general, it's a problem that is related to every environment that contains a fairly high amount of humidity and together with a fairly low temperature. So the main tool we have to understand icing processes is the classical theory for nucleation processes. So icing can be regarded as a nucleation process, which means that it can be described as a spontaneous arrangement of water molecules that come together to form what is called a nucleus. If this nucleus is large enough, then it becomes stable, it doesn't melt away, and from that point on, when it reaches its critical size, it is possible, it becomes stable and it can grow further, and the actual phase change can take place. In order to understand how likely is for this process to happen, we can compute the energy gap between the initial and the final state of our system. The initial state being we have no nucleus or a very tiny one, and the final state being a nucleus of a certain size. The energy profile, the energy gap rather, is made up of two contributions. The first contribution is the energy required to build the interface between the water phase and the ice phase. So while the second contribution is the energy released when the nucleation actually happens and the nucleus grows. As you can see from the green dotted line is the energy profile I'm talking about, and it has a minimum for the vanishing radius and a maximum called the critical radius of nucleation, after which, since the slope is negative, further growth of the nucleus is actually encouraged by the physics involved. This is what is called homogeneous nucleation. We're not taking into account the contribution that the substrates or the surface on which nucleation happens can provide. When we want to take into account the surface as well, so the substrate contribution to the process as well, we want to add another term to the nucleation energy profile, which is the energy required to build the interface between the substrate and the ice. For really simple substrates, for example, such as flat ones or spherically convex or concave ones, it is possible to write the heterogeneous nucleation energy profile as a function in terms of the homogeneous nucleation energy profile, just by multiplying by a factor which encodes the geometry of the substrate on which the nucleation is happening. And this factor depends on two parameters. One is the sign of the contact angle, and the other one is the ratio between the radius of the nucleus and the radius of curvature of the substrate in that point. Since f is always between 0 and 1, we can see that the heterogeneous nucleation energy profile is considerably lower than the homogeneous one, which means that this barrier is also lower, which implies that an heterogeneous nucleation process is way more likely to occur than a homogeneous one. Another important quantity we would like to introduce is the nucleation rate. Nucleation rate is a quantity that measures the amount of nuclei with I water molecule in them are produced per unit volume each second, and this definition is given by assuming the ice nuclei can only grow or melt one water molecule at a time. So basically, we want the net amount of ice nuclei that jump from the I-1 state to the I state, minus the amount of nuclei that jump down from the I state to the I-1 state. And the probability of this jumping to occur is proportional to the average number of molecules W that crosses the interface at any given time. The water molecules themselves have a random movement which cause the nucleation to take place in the first place, and this basically is an average of that movement, and it is also we assume it's also proportional to the surface of the nucleus itself. So how likely is for one of these random molecules that it's moving to cross the surface and attach to the nucleus? Using classical nucleation theory, it is possible to estimate values for this quantity, and across many years they will, in good accordance there was good accordance between experiments and theory. Another thing we can, another sensible assumption we can make is that the C is the concentration of water of ice nuclei with I water molecule in them. The rate of change of the concentration can be written as a function of the nucleation rate this way. Now, for a large number of molecules, or for big nuclei, we can regard those nuclei as being spherical. Therefore, basically, the number of molecules I in them can be regarded as the volume of the nucleus itself. This is called kinetic continuum approximation of the problem, and it basically lets us take a continuum limits of these expressions. And putting those expressions together, what we find is we find that we have a Fokker-Planck-like equation for the concentration of nuclei. If we regard C as being kind of a probability density function when suitably normalized. So essentially we're taking a problem that is described with using statistical quantities such as the concentration of ice nuclei, and we want to translate that in a dynamical sense. So we want to describe the actual movement of the water-ice interface, associating to this Fokker-Planck equation a stochastic differential equation, as it is usually done. In this new picture, we're looking at the motion of the interface when it's subjected to the energy profile itself, which still appears here, and to the random motion of molecules I mentioned before. So when we describe these random motion of molecules, and specifically the motion of the interface itself, we can compute how it's likely for the system to jump from its initial state, whatever it is. The vanishing radius is one good choice, to its final condition. So we can assume which we can assume to be the interesting one is its critical size. In order to do this, since we have a random contribution from a stochastic variable, we can take into account all the possible paths the system can take in order to jump from its initial state to the final state, where the paths similar to the classical trajectory count more than the weirder ones. Using this transition probability, it is also possible to compute another important quantity called the mean first passage time, which is the average time that it takes to the system to jump the barrier. This is the main quantity that can be compared to observation and experiment, because it's with high-speed cameras it can be easily spotted and measured. Well, not easily, but it's kind of a complicated thing, but it's still possible to do. Now, the limitations of the classical approach are two mainly. There is a limitation regarding the growth of the nucleus. I only talked about a single variable, the radius of the nucleus. So the classical nucleation theory only allows for a spherically symmetric growth of the nucleus, which is not really a big problem by itself. While the second limitation is the probably interesting one, because classical nucleation theory only allows spherically symmetric substrates to be described this way. And since we want to know how, in principle, ideally, we want to know how icing processes are related to the geometry of the substrate, this is a big drawback of the theory. There are ways in which we can avoid this problem. Namely, we can use molecular dynamic simulations to kind of solve both of the issues at the same time. Molecular dynamic simulation, as I'm not an expert, but basically the core principle is that they model the behavior of each single element in the system, both the water molecules that build that make up the water phase, and the molecules of the substrate as well. So the idea is to solve Newton's equations for each single molecules, taking into account the interaction between the molecules, which can be usually of two types, either non-bonding, like Lennard-Jones potentials or Coulomb potential and so on, or bonding, like which are potentials that model the chemical bonds between the atoms inside the molecule. The result of the molecular dynamic simulations are actually astounding. They let us actually see the nucleation process while it happens, and they have in a wide range of cases, not only for water molecules. The big drawback in this case is that they take a lot of time to finish. So they're not very efficient in probing a wide range of possible geometries in our case, because we have to fix the geometry of the substrate previously at the beginning of the simulation itself, and then run the simulations. So another route we can take is to kind of extend our classical nucleation theory in order for it to embrace a wider range of possibility regarding the substrates. But in order to do that, we have to solve also the first limitation the theory has, which is we need to allow the nucleus to grow in different directions independently. So we need to basically have more than one variable for the description of our system. So the idea is starting from the stochastic description I mentioned before, looking at the motion of a two-dimensional surface, the two-dimensional ice-water interface, subject to a force caused by a functional, with an energy function that describes the energy each state of the system has, plus a noise that I will introduce later on. This part here basically mimics what we did, what I showed you regarding heterogeneous nucleation processes. As you can see, there are three terms that made up this functional. Again, the first is, N, by the way, is the normal vector field to the interface, while NF is the normal vector field to the substrate we are choosing. And in principle, we can choose whatever geometry we want, as long as we can express it as a function of the XY coordinates. Well, basically, the three contributions are the energy necessary to build the ice-water interface, the energy required to build the substrate ice interface, and the energy released during the nucleus formation. Exactly, that mimics exactly the heterogeneous nucleation theory. By taking the minimum of this functional, we can find, as usual, the Euler-Lagrange equation that tells us that the minimal configuration for such a system is a sphere. No surprise about that. And the boundary conditions give us kind of a generalized Young's law for contact angles in this case, where this would be the cosine of the contact angle point by point. So starting from this kind of picture, this framework, this description of the system, we can postulate kind of a set of a system of stochastic differential equations that we think describe the system at best. this system must have as a limit the classical nucleation theories, of course, and we add 3 stochastic variables that basically are a Markovian noise with white Markovian noise with Gaussian distribution. Since we don't know much about the noise the system has, this is the best guess we can use, also the easiest choice we can make. And in a similar fashion as I showed you in case of a single stochastic variable, we can sum over all the possible ways the system have to jump from the initial to the final state. But in this case, it means summing rather over paths. It means summing over all the histories the system can experience while transitioning from the initial to the final state. On the left hand, the image on the left hand side is just a drawing taken from an article in string theory, in which I know that both in QCD, effective theories for QCD and string theory, they use kind of similar approaches. So that's where I look for drawings there. And on the right hand side, you can see a snapshot, 3 snapshots of a solution of an equation which is closely related to the system of equation I showed you, which is called the Carter-Parisi-Tsang equation, which revolves around understanding how substrate of biological substance grows by deposition, which is a similar problem to what we are trying to describe. The transition probability gets generalized this way, and again, history is similar to the classical trajectory, to the classical history, count more than the weirder ones. By finding the transition probability between the initial and final state, it is possible to estimate the average time that it takes the system to escape its minimum and reaching its critical size, and for the rest of the phase change to take place. A last couple of words regarding observation and measurements. A big acknowledgement to my colleague Michael Gritzen in the mechanical engineering department, which built this amazing, tiny but amazing machinery. This is a way of taking actual measurements of what we're trying to model. The idea is to measure the mean first passage time, so the time that it takes for a system for a droplet to start freezing, by depositing droplets with a syringe on this rotating plate on different substrates, and filming it with a high-speed camera for a long time. Usually it takes half an hour, maybe more, for the system to for the nucleation to take place. So we need to wait a bit. While droplets are roughly around 1 millimeter to 2 millimeters in radius, so they're rather small. This machinery, basically silicone oil, really cold silicone oil gets pumped into these pipes, so this environment can get cold down to -30, -35 degrees Celsius, and the transparent casing is chosen in order to be able to film the droplets. There is a gap in between that allows higher insulation once the air is taken out of it, and this is the same image from the top. As you can see, the rotating metal plate and the pipes that goes around in order to uniformly cover as much as possible the chamber inside. And then lastly, thermocouples. I believe 3 or 4 thermocouples are used to take track of the temperature inside the chamber, so that it can be as uniform as possible. And this, of course, makes measurements more accurate. Thank you. That would be all.
Thank you. We have 10 minutes. Yeah. Oh, yeah.
Hello. Thank you. You talked about condensation processes as well as about the water droplet itself freezing. I wondered if you see your approach towards the initiation of the solidification both as valid for the vapor phase as well as for the liquid phase, and even for the three phases together, how that might...
Yes, actually, this kind of reasoning is this kind of reasoning is take from the theory behind condensation. So the original nucleation theory is built from...
Are you familiar with this theory? I understand this, but you've been speaking about the formation of ice from vapor phase, and you've also been talking a little bit about the formation of ice in a liquid continuum, as I understand it.
Yes,
I just wanted to get into the next bit of it, beyond yeah, okay, perhaps I didn't understand all of it.
The particular condition I'm trying to describe are kind of two sub-steps freezing processes in which, for example, we have a humid environment, water condensates on a surface, and then it freezes afterwards. It is possible to describe, like, I don't know the actual term in English, unfortunately, but basically from vapor to ice instantly, I believe.
Yeah, which is why we see these beautiful faceted things like snowflakes, where you're getting a different sort of process from when you're getting water freezing.
The problem with, well, it's not a problem, but it's kind of a complication with that, is that when we write this equation here, another term appears. It's the second one, which is only present if we are not in super saturation conditions. And from water to ice, I would assume we are not in super saturation conditions, while between water and ice we are in super saturation conditions. And this term in particular tends to get tricky to not in the one-dimensional model now, but in...
So yes, it's a strong analogy, but slightly different terms depending on whether you're moving from the vapor phase to ice, or from the solid, from liquid water into solid ice.
Yes.
And you don't have the direct desublimation, right? You're not looking at...
we're not considering sublimation now.
Very limited problem. Freezing directly from supercooled liquid to so far.
Yeah, right.
You may have noticed that I didn't show you any comparison between results and math. I only showed you the idea behind it. That's because it's still we're still tackling the problem, so we don't have numbers yet to back this kind of description. But once we kind of successfully solve, so to say, this this kind of the description of the problem, it is maybe possible to complicate things further and take care of sublimation and freezing from vapor to from vapor as well. Yes.
Yeah.
Just a question about the experiment. In the experiment, you
place droplet of water with room temperature into the cold conditions. Yes? Not?
Yes, I'm not the one that takes measurements personally. The condition we want is to lower the temperature, is either to put the droplet here and lower the temperature very slowly, so that, because if we drop the temperature very fast, nucleation can take place just because of the shock. So we either can put the droplet and slow and lower the temperature really slowly, or put to lower the shock as much as possible. Yeah, I don't think it's advisable to put room temperature water droplet on the plate, on the cold plate right away.
I'm asking because I think that in reality you have like droplets of overcooled water, and this overcooled water and even water with temperature close to the freezing point include many clusters similar to ice. So therefore, nucleation will start not from just simple water molecules, but from some clusters which already exist. And if it's possible to reproduce in this condition, maybe it should.
It may be. It's I would assume it's. So we're looking at a very particular scenario here, in which we have a bulk of completely pure water, and we want to measure how fast nucleation processes happen inside the bulk of the water, in contact with the surface. Again, probably it is possible to then get closer to reality, but measurements as they are in this controlled environment are quite tricky to take as they are. So, but yeah, I understand the point. Thank you.
Okay. I have a question. There is technology, it's called spray coating. It's you take a very bad metal, very bad material, and then coat its surface with very good, very expensive material. So it's then in for some say applications, the only surface of that body say detail is important. It's toughness of that surface, not what's inside. So that is very, very good technology. And to do that, they use the many droplets and accelerate them by explosion or by jet through aerodynamics. And these droplets, they hit the surface and a little bit penetrate, splash, not splash, but spread on it. It should spread and solidify. Okay, and to make the surface good, the solidification should be quick. Right? So they call it. I'm not sure again that it's in English to get amorphous material like glass. Right? So the droplet and material has no time to make crystals. Mm-hmm. So that is what I believe you call heterogeneous, not solidification, icing. Because what you explain is very close. It's ringing about that solidification of droplets. They are huge. I mean, it's an industry. Based on that, so there are many papers. In particular name, just one name, it's Megaidis from US.
Yeah, it's actually one of the contributors of the it's this image here, among others.
Okay.
So I can say two things regarding that. The first thing is. Probably with spray coating, what Frank mentioned was more relevant since we have actually moving fluids, and but for sure the shape of the surface beneath that we want to coat may affect how fast the solidification process happens. The second thing is that actually, and Manish after me may mention this in particular, because in the lab in which the measurement probably will take place, they study spray coatings in order to achieve super hydrophobic and super hydrophobic coatings again, and the shape the coatings acquire, one, it solidifies. It may not be completely homogeneous, and it may also depend on the procedure that it is used for the coating to be done in the first place. And since it's not a homogeneous surface, it's not completely flat, that may affect how icing processes happen on the surface itself. So that's why it may be interesting to understand the relationship between icing processes and geometry of the substrate and when the processes occur.
So we should close the discussion. It's already time for the second presentation. However, after second presentation, we will have break and then 1 hour for discussion. So you can think about extra questions. Please do not forget that Frank also did part of that presentation, so he also should be asked. In particular, what's the difference between icing of aircraft and icing of ships? Is there a difference? I believe it's a good question, but that is but that is for discussion section. So thank you very much. Thank you, Davide. Thank you, Frank. And